Hi there, welcome to this session about what the CRaC coordinated restore at checkpoint on the Java virtual machine. So first of all, just a few words about me. So my name is Gerrit Grunwald. I'm working as a developer advocate for Azul Systems. And I have a background in desktop Java a lot, but also do backend stuff. And I mean, I love just coding. But let's go to the topic. Java is great. We all know that. It has a vibrant community because that's one of the reasons why we are here, right? We have this great conference like this one, and we have hundreds of Java user groups. We have thousands of free open source software projects. But the real star of it is the Java virtual machine, right? And the question is, how does it work? Let me give you a very simplified introduction on how the JVM works. And we will just take a look at the specific part. So let's say we have this Java file with the source code, and we put that into the Java C compiler, and then it creates a class file, which contains cross-platform bytecode. And then we take this bytecode and use a class loader to load the bytecode into the JVM memory. So once it is in the JVM memory, it can get from there into the so-called execution engine. And you already see the execution engine is just a word for lots of different things. And there are, for example, there is the interpreter, the C1 JIT compiler, formerly known as the client compiler, and the C2 JIT compiler. This is known as the server compiler. And then there is a profiler and there is a garbage collector. But we will only focus on these three parts, the interpreter, the C1 and C2 JIT compiler. And the two compilers are also now so-called doing a tiered compilation. This is since JDK 7, it made its way into the JDK, and from JDK 8 on, it was the default. So today we always have tiered compilation, and I will come to that a little bit later. So if we continue on how does it work, then we have this bytecode, and we have the interpreter. And the interpreter takes the bytecode and converts it into the construction set of the CPU at the current machine. And the JVM is, let's say, looking at it, and it's counting method calls, right? So, and if a method was called a specific specific number, then it reaches this threshold, and then the JVM takes this hot code, the hotspots, so-called hotspots, which is one of the reasons why the hotspot compiler was called hotspot compiler. It takes this hot method and passes this to the C1 JIT compiler. The C1 JIT compiler compiles this code as quickly as possible with very low optimizations. So the main goal is to create compiled code as fast as possible. Remember, this is the old client compiler. And the reason for that is, of course, if you have a desktop application, for example, you would like to start it up like this, right? You don't want to wait for super high optimization, but you just would like to have your application started. Well, once it's running this compiled code from C1, it will be profiled by the JVM again, and the JVM tries to detect, let's say, hot code, right? So that's again something like method calls, and it will be checked how often will this compiled method be called. And if another threshold is reached here, then it will take the code and pass it. So it passes the hot code to the C2, or formerly known as the server compiler. So the server compiler compiles the code with the best possible optimizations. And you can imagine this takes more time. So it's slower than the C1 compiler. And after that is done, we have the optimized code, right? And this is called tiered compilation. So we have the C1 compiler, and then if the C1 compiled code was hot enough, then it will be passed to the C2 compiler. So this is called tiered compilation. And there we have different levels of execution. So if we speak about level 0, then that means this is the interpreted code. Then we have level 1, which is compiled code without any profiling. Level 2, C1 compiled code with basic profiling. And level 3 is C1 compiled code with full profiling, which has a little bit of an overhead. And then there is level 4, which is a C2 compiled code. And this uses the profiles from the formerly compiled code. So the preferred way of using it is interpreted code, level 3, and then level 4. Mainly, this is the transfer, or let's say the transitions that is mainly used, if possible. There are others, but we don't want to look into this in these other transitions. So that leads us to the so-called execution cycle, or I name it execution cycle, which is we start with the interpretation, which is slow, execution level 0. Then we have finding the hotspots, so profiling the interpreted code, method counting in this case. And then it comes to the C1, fast compile, low optimization, which is execution level 3 in this example. And again, this will be profiled, and we try to find hot code. And then the hot code will be compiled by C2, which is slower in compiling, but has higher optimization. And then there is this other thing that can happen, and that is called de-optimization. So de-optimization, let's take a short look into that one, because it's good for understanding. If this is our code, so we have just an if-then clause. So if the value is larger than 0, then the result equals 3, and we print the result. If it's equal or lower than 0, then the result will be 0, and we print the result, okay? So if the profiler figures out that mainly we have values larger than 0, then this is the hot path. So it's always 3. So the compiler will optimize the code in a way that it will directly set result equals 3 as long as the value is larger than 0. If it's equal or smaller than 0, it will do a de-optimization. That means the code, the already optimized and compiled code from C2 will be thrown away, and the whole thing will be again interpreted, C1 compilation, C2 compilation, and this time with both ways, right? With the value equals or smaller 0 and larger 0. So this is the optimization, and you can imagine that this takes time, and this costs its performance. It's a performance hit. So you would like to avoid the optimization. That's the main thing. So that's all great, right? So this is really cool, the JVM, how it works. But the problem is it takes time, right? So if we take a look at the JVM performance graph, where this is level 2 to 1, which is the optimum performance in this case, we see we have these 3 colored areas here, whereas the yellow is the interpretation phase, and we have the green one, which is the C1 compile, and then the blue one is the C2 compile. So, and this area from the beginning until we reach the highest level of performance, this is usually called the application warmup. Some people say JVM warmup, but this is in principle your application being compiled, optimized until it's perfectly optimized. And then you see these reoccurring gaps once it's optimized. And this is usually garbage collector pauses. And then there is another gap in the warm-up or optimization phase. And these are the de-optimizations. That means before one of those gaps, there was already optimized code. And then somehow it was found that, oh, this optimization is not really working the way it should be. So the code was thrown away, and then you see the hit in the performance because interpretation again, C1, and then again C2. And so after some time, everything is optimized at the best possible way. Okay, so that means it needs some time to warm up and optimize the whole application. This is all good, but if you think about microservice environments that we have today, then it would mean if we run the service the first time, we have to warm it up. Second time, we have to warm it up. Third time, we have to warm it up. And you can imagine with all next runs, we always have to warm up the JVM. That's a bit disappointing, isn't it? Wouldn't it be great if we could do something like first run, warm up, second run, full power and fully optimized, third run again? That would be the ideal world, right? So what can we do to make that happen? Wait, there was something called class data sharing, or CDS. This might help in starting up faster. Okay, so class data sharing, there's app CDS and dynamic CDS. These are the two main cases where you can use that. And in principle, it's dumping internal class representations into a file, and this file can then directly be loaded. And these files are shared on each JVM start. So that means you do it once, and then the next time this file is needed, you can directly load it from the representation that is stored into the file. There's no optimization or hotspot detection because this all happens before the whole compilation process starts. And this only reduces loading of classes, the loading time. But still, if you have huge applications with big frameworks and lots of dependencies, it couldn't speed up the loading or startup time by 1 to 2 seconds. So which is still, it's good, but you have to keep in mind it's already per default enabled. So it's in there, I think, since JDK 12, if I'm right. Okay, and it happens here. So that means we have the bytecode, then there's the class loader, and at that point, CDS is really hitting or making the whole thing faster because it accelerates the class loading. But after the JVM memory, then all the execution engine interpretation and compilation phase starts. So it doesn't really have any effect on optimizing code or warm up really of the application. Okay, and there's this other thing called ahead of time compilation. Well, this might be a good idea. Let's take a look at that one. So why not use it, right? Why not use AOT? So we don't have to interpret bytecodes anymore. We don't have to analyze hotspots. There's no runtime compilation of code, and we can start at full speed straight away. And GraalVM native image does that, right? So problem solved, right? So I saved you 30 minutes and we are done. Not so fast. AOT is by definition static. So that means the code is compiled before it is run. And the compiler has no knowledge of how the code will actually run. Keep in mind, we have these optimizations that the JIT can do. With the compiler, it can do some optimizations, but not really during runtime, right? So it's just upfront. And there is something called profile guided optimization, or PGO, and that only helps partially. So if, again, we take a look at the JVM performance graph, and now this time try to apply AOT compilation, then it might look like this. So this is just, it really depends on the applications and everything. So this is just as a hint. So you might get up to 60% the speed of the fully optimized JIT code, right? The AOT compiled code. If you then use PGO, so profile guided optimization, you might also increase it by another 20%. So you can maybe reach up to 90, right? But for this, you have to keep in mind, you need at least run it once for the profiling, because the profile guided optimization, the word itself tells you you need a profile to optimize the code. So you need at least one warm-up run, okay? And still you won't really be able to get the same performance out of it. So if we compare it side by side, then it means the AOT can't make use of method inlining heavily like the JIT can. And there's also no runtime bytecode generation. Reflection is not that easy using AOT. It is possible, but not really good. You can't use speculative optimizations. Overall performance will typically be a bit lower than a JIT compiler. And one of the biggest problems is that the deployed environment is not the same as the development environment. So that means all tests might pass in your IDE. Once you create the native image, it might fail. So this is one of the biggest problems. On the other hand, if it runs, you have full speed from the start, where the JIT needs warm-up time, and you don't have any overhead to compile the code at runtime, where the JIT needs this overhead in the beginning for compilation, optimization, and all these kind of things. Okay, so the JIT disadvantages are probably it requires warm-up time and the CPU overhead to compile code at runtime, right? This is not really the good parts. Okay, if you take just a short look, JIT optimizations, I said that the JIT optimizes the code. I just picked two. So one of the big ones is inlining. What does it mean? So if we have, for example, a method that sums up a value to a given value, so let's say I put in sum up to 10, and then it will just run a loop from 0 to 9 and just increase this by 1 all the time, and then return the sum. And it will call this method add, where you just have 2 parameters, 2 ints, and you just add these 2 parameters, and that's the whole thing. So that means if this is the original code, the inline code would look like this. So instead of calling the add method, the profile or the optimizer figures out, oh, This is just adding the one value here, and then it just directly does it, right? So instead of calling, so you save the whole calling of the other method all the time, and that saves a lot of time. This is just a simple example, and there are more complex ones, of course. Then another one which is really interesting is loop unrolling. And that means if we have, for example, a method like this one, which just checks a given integer number for prime, and we call this method 1,000 times, right? Then that means every time in this loop, it has to go and jump internally and call this method. And this loop that we see here, if you unroll it, it would look like this. And I did that. And even on my M1 Max Mac, which is really a powerful machine, it nearly was twice as fast when I did this. Exactly that what you see there. I did that. I just called this loop instead of once in a loop. I just called the method all the 1,000 times, and it was so much faster because you just save this jumping in the code. And that's really interesting. So you really can gain a lot of performance with all these JIT optimizations here. And you never forget that this is happening at runtime. So that means if the behavior of the application changes, the JIT can react on that and can optimize code according to your behavior or the application behavior, which is interesting. But now we saw App CDS, we saw AOT. Let's take a look at a different approach. And there is a project called CRaC, which is checkpoint restore in user space. And this is a Linux project, and it's part of the kernel since 3.11. So this is it's since 2013. So it's quite a while in the kernel. And it was made to freeze a running container or application, then checkpoint its state to disk, and at another point in the future, restore this container again from the saved data back into memory. That's the main idea. And it's already used or integrated in OpenVZ, in Linux containers, in Docker, Podman, and others. So it's really something that is not new, right? It's there and it will be used. Maybe you already used it and you didn't even know. It's mainly implemented in user space, not in the kernel. So the main goal is migration of containers for microservices. Just keep in mind when they started that, it was 2013. And we have 2022, and now I'm talking about that, and it's in there for so long, right? So they had this idea long time ago and implemented it. It's a very nice project. It heavily relies on the /proc file system, where it gets all the information from, and which is also one of the problems because this is not available on Mac, for example. It's also not available on Windows. So that means this is at the moment only available on Linux, right? So, and it can checkpoint processes and threads, application memory, memory map files, shared memory, open files, pipes and FIFOs, sockets, interprocess communication channels, timers and signals, and it can rebuild the TCP connection from one side without need to exchange packages. So it can really re-establish the TCP connection. It's very fascinating. It also comes with some challenges. So you can imagine restarting from a saved state on another machine is not that easy. So that means I create a checkpoint here, then transfer it to another machine and try to restore it there. This is tricky, not so easy. Another thing would be starting the same instance multiple times on the same machine. Also, it's possible, but it's a hack because the PID of the process will also be restored. And this is only once on a machine because it's unique. So that leads to problems. And if you would just use it on a Java virtual machine, it's not that easy because the Java virtual machine would assume it's the only thing running, right? So how can you stop me and restart me? This is it doesn't really work like that, right? So because the applications running on the JVM need also have maybe open files, open sockets, so you can't. It's hard. You can't really do that easily. And that leads me to the CRaC project, which is a coordinated restore at checkpoint. This is exactly what I tried to explain. If you have a JVM that runs applications, then these applications have open files, open sockets, open database connections. You can't just simply shut it down. So you need to make the JVM aware of, you will now be checkpointed, you will now be restored, something like that. So Creo comes bundled with the JDK. So CRaC relies on Creo, but it's encapsulated. So that means if there would be something else, we could also use that. So it's not really heavily directly bound into Creo. We just use Creo. It could be something else on another platform. It's all possible. The heap is cleaned and compacted, so the JVM is in a safe state. It throws checkpoint exceptions. So in case of open files or sockets, the CRaC project or library will let you know that you made a mistake and will tell you, oh, there is still something open in that file or whatever. It comes with a very simple API, and it creates checkpoints using code or JCommand. And it uses the JVM save point mechanism. This is the same that is also used for the Stop the World garbage collection. So if you have questions or ask yourself, oh, wait a minute, if I have a multi-threaded system, so how can it just stop it and create a checkpoint? It uses the same mechanism that will be used when the JVM stops everything and does a garbage collection. So this is not a problem, but that gives you an idea that it has to be somehow be part of the JDK itself, right? So you can't really just load something, a library or which does all the stuff. So it's part of the JDK, which means it is an open JDK project. So this is not something that is only available from Azure, because this is really an official open JDK project. You can find it under openjdk.org projects CRaC, and it's led by one of our engineers called Anton Kozlov. So you can check it out there. It's an official project, and the stuff that you can download there, and that I will show you later on, is an OpenJDK built from Oracle OpenJDK. So this is not Zulu or something. So it's really it's OpenJDK. So I already told you that using CRaC means the application needs to be aware of being checkpointed, and when you restore it, it also needs to know, oh, you have been restored, right? To make sure that you can close files, close sockets, close database connections, and re-establish them after the restoring. Starting a Java application is the same as you usually do, with the -jar and then the name of your jar, and you just add -XX CRaC checkpoint 2 equals, and then you put in the path where it should store the checkpoint. And for the restore, because what will happen is it will create the checkpoint and shut down the JVM. If you would like to restore it, you just call Java -XX CRaC restore from and point it to the same path where you have stored the files. And this is interesting because you can also think about creating checkpoints for different use cases. Sometimes in some applications are used from one department, and then the same application will be used in another department in a totally different way. So that means a checkpoint could be different because different modules will be used, right, and optimized. So you could create multiple checkpoints and then start them just by pointing to the right folder. The API I already mentioned is pretty simple. It's just one interface. It's called resource, and it has just two methods: before checkpoint and after restore. And you implement that in principle in all classes that have resources, like database managers or whatever managers you use to connect to the internet or to other APIs or whatever, where you have open sockets or open files. There you implement the resource interface, and then there is a mechanism that to make sure that the checkpoint, before checkpoint and after restore methods will be called. And the resource objects, where you have implemented the resource interface, they need to be registered with a context so that they can receive notifications. And for that, you can get from the core class core.getGlobalContext, right? This is a static call. You can get it there and then register your resource. So that means you have your class, you implement the resource interface, you register it with core getGlobalContext. And the global context then maintains a list of all the resource objects, and the before checkpoint methods are called in the order you add them, right? So if you register them to the core context, in this order, the before checkpoint methods will be called, and the after restore they will be called in the reverse order to make sure that everything is in the right place, right? Because it could be possible that you have resources that depend on each other. So then you need to make sure that they are established in the right way. You can do that programmatically. There's a method core checkpoint restore. You might ask yourself, why do I need to do that programmatically? Sometimes companies already have code to warm up the JVM. And with this, you could just, when it's warmed up, you can just create the checkpoint automatically from the code. Or you can also use a J command to do that. So now let me show you a simple example. And it's really pretty simple. It's a scheduled thread, and that calls every 5 seconds a loop. And in this loop, it will be 100,000 times create a random number, and then it will check if this random number is a prime number. The first thing that will happen is it will check if the result for this number is already in the cache. And if it's in the cache, then it will directly return the result, true or false. And this is quite fast because it goes directly from memory. If it's not in the cache, then it has to calculate for each number, is it prime, get the result, store it in the cache, and then return it, which is, of course, slower than the first way. And to make it more realistic, every 60 seconds, the cache will invalidate values that are older than 60 seconds and will just wipe them out. So, because that's what usually happens in your application too, right? So you cache some stuff, and after a specific timeout, the old stuff will be cleaned up, right? And this is the same in this application. So that means the first run is slow because the cache is empty. And then the time to check this 100,000 random numbers should really decrease with every run. That's the expected behavior. And I did some tests on a machine, and then it looked like that. So after 9 iterations, the normalized performance was around 1. So then it was more or less stable and optimized. So let me show you a little demo. And I do the demo first in the slides. So we have 2 shell windows here. And on the left window, this is where I call the jar file. It's just called CRaC4 jar. And I pointed to the folder CRaC-files. So this is the folder where it should store the checkpoint files. So then I run it. And the first run is quite slow because the cache is not filled yet. You see after the run, it's 63% filled with values. So, and it took 27 seconds in this case. The second run is faster, and then you see with every run, it gets faster and faster and faster because the cache is more and more filled. And then at one point here, for example, it's fast enough. And I say, okay, now it's fast. Now let's create the checkpoint. So in another shell, I just call J command CRaC4.jar jdk.checkpoint. And this will then lead to this. The JVM will create the checkpoint. I put some system out print lines there in the main class and in the generic cache. These are my 2 resources to show you the order of calling. And you see that it will give me, on the right shell, it will give me the PID of the process, and you see it on the left one too. So this is you could also stop it or create the checkpoint by calling the PID. It's also possible. So, and once it's done, it says command executed successfully on the one shell. On the other one, you see CR colon checkpoint and then killed. The JVM shut down. So, and this, all this runs is more or less the application warm-up time that we see. And then if I would like to restore it, I call it java -XX CRaC restore from /CRaC files. And now you should see, it should continue counting with 12 and it should be directly fast, right? And you see what happens. First, you see the printouts here. It's in the reversed order. First, the generic cache was called, then the main. And the run time here was again fast. So it's not exactly 17 milliseconds. This differs a little bit, but you see it's still fast. The cache is still filled and it continues running with the same speed. And the good thing is now I could restore it I could stop it now and restore it again, and it would be the same. It would start from 12. So that means the whole JVM startup time or application startup time is just gone. It's stored in these files, and I can restart from there. So that means creating the checkpoint, I can do it like this, J command, then your jar file name and jdk.checkpoint, or I can do it from code with core.checkpoint restore. If you would like to play around with it, it's on GitHub. It's github.com/hansolo/CRaC4. There you can find this demo example to play around with. And okay, so that's nice. It's a nice demo. You know, I created the demo, so I can fake it. It's fast. Of course, it's fast because it's my demo code. Well, we also created some demos that you will find on this on the CRaC, the github.com/CRaC repository. And we did some demos with Spring Boot, with Micronaut, with Quarkus, and there's also an XML transform. And these are the times in milliseconds running on OpenJDK. So that means Spring Boot was around 4 seconds, Micronaut around 1 second, Quarkus a little bit faster, just below 1 second, and the XML transform was 4.3 seconds. So now let's see how the times decrease when we use the CRaC OpenJDK. Aha. So as you can see, it is in principle in the same range. It's always below or around 50 milliseconds. And the reason for that is that it's really just loading the stuff from memory, from the disk into memory, and that's it. And that's the reason why it's nearly the same speed. Of course, it depends, because if you can imagine if you have to restore a lot of resources like sockets, database connections, read or open files again, that might take a little bit longer, but still it's much faster than warming up the JVM. Okay, so you can find the demos also on the GitHub repository. So as a summary, CRaC is a way to pause a JVM-based application in a controlled way, and you can restore it at some point in the future again. And the benefit is potentially extreme fast time to full performance level. And it eliminates the need for hotspot identification, method compiles, recompiles, and de-optimizations, because that's all done in the warmup. And after that, we create the checkpoint, so we don't have to do it again. We have improved throughput from the start, and CRaC is an OpenJDK project. And at least CRaC can save infrastructure cost. So let me just give you a short example on how it can save infrastructure cost. If you have the CPU utilization on the y-axis and the time on the x-axis, then usually this is what you see when you start up a JVM in a container. First of all, you have a high CPU utilization, and then it drops, and then it levels at a specific level. So this peak is the JVM warm-up time, and the overhead is more or less the interpretation and compilation overhead, because the CPU has not only to run your application, at the same time it has to optimize it using the interpretation C1 and C2 compilers. So if we create a checkpoint here and start the next time from there, we save the whole overhead. That means you just need, for one time, you need to, for creation of the profile of the checkpoint, you need a higher CPU or high power CPU. But after that, you can run the same stuff on a lower CPU node, which saves a lot of money. Because most of the times the high power CPU nodes are expensive, and the memory is not the big of the problem in the cloud. And this eliminates the warm-up time and the CPU overhead. Like I said, github.com/CRaC. There you can find everything. And there's also a wiki.openjdk.org display/CRaC, where you can find more information about that. And with this, I think I don't have time for another demo. I think I'm done. So if you have questions, then feel free to let me know.
Wow, Gerrit, you rock. Actually, it was really deep dive into JVM internals. Thank you very much for all that stuff. And no surprise, there are few questions from our participants. So let's start with the first one. From your experience, which kind of projects really care about startup time? The obvious cases are high-frequency trading and maybe stock exchange. So what do you think, where it's applicable?
No, I think it's a lot of applications can really benefit from a startup time, for improvement in startup time, because if you think about, you have all these very low power nodes these days, and you would like to run a Java application in a container on that node, then usually what you see is, if you think about AWS Lambdas, for example, they really suffer from startup times because they just need to do a little bit of code, but warming up and starting up the JVM takes so long that it's a cost factor, right? So if you have time and money, you don't care, but usually you would like to save money, and the cloud stuff is not cheap. So if it can be faster, and if you can reduce startup time from seconds to milliseconds, that means the CPU time that you pay for nodes will decrease from seconds to milliseconds. And the more you do that, it really sums up, and that means a lot of money. So you really can save a lot of money with that.
Great example. And another thing I think in this context is that we usually, if we are not talking about serverless, we usually restart our applications when in microservice world when we deploy new versions. In this case, can we restore some state, some cache that will help us, or it's completely invalid and we should start from the scratch?
If you haven't, yeah, that's a good idea. We also thought about that. I think you mean something like incremental caching, like you have a running application, then you do a new version. Do I have to really flush the whole cache and create a new checkpoint? Yes, you have. At the moment, you have to do a complete checkpoint again. But we also thought about that, just doing incremental steps, right? So if you have a checkpoint, then maybe figure out what has changed. But it won't really work, I guess, because what we really save is the state of the JVM. If you, including your application, if you change the application, it's not easy to do just a diff of against a new version. So if you have a new version, and then I think you would need a new checkpoint for that.
I see. We have also a question from Luis. Thanks a lot for this presentation. I might have misunderstood by why can't ahead of time compiler optimize using inlining and loop unrolling?
Because the code will be compiled directly. So if you have a JIT compiler, then that means the code is profiled during the runtime. So that means once the code is touched, it runs, and then it will profile and check, okay, oh, this is now running in that way, so it can optimize it, right? There are possibilities of optimizing code, especially with the new compilers for sure, but it's not the same. The problem is you can't really optimize at runtime. This is what I would like to say with these optimizations like method inlining and loop unrolling. Of course, this should be possible by doing it with a ahead of time compilation tool, probably. But the main part is, let's say, if you use CRaC, for example, then you can create a checkpoint, and then if you start from the checkpoint again, you have still the complete JIT. So that means you get startup times in the range of GraalVM native image, with the benefit of being able to still optimize. So if the application changes its behavior during runtime, because maybe more customers use a specific part of the application, then the JIT can further optimize, which is not possible using AOT compiled code, right? So there you can just compile it one step. This is the one look. You can optimize and then run it forever. And if the behavior changes, there's no way to interfere with that anymore. That's the main reason.
But maybe ahead of time a compilation in fact uses inlining somewhere under the hood.
Yeah, probably. Yeah, it will probably use it too. It's just not possible doing that at runtime, right? So maybe I should say more clear. Yeah.
Yeah. We have also another question. It's maybe something about related to security. What is the guarantee that we will pick up the right class file? And can it be used for some property changes in real time?
This is not really related to CRaC, isn't it? If you have the class files and class loading, this is what we really do with CRaC is we take CRU as the part that is able to store this stuff into files, and it saves the state. It's not that it really saves your code or something. It's really the running JVM that will be stored in files. And I didn't have the time to run the demo there. So then you can see the number of files that will be stored. It's a lot of small files, and then there was one big file. In this case, it was 32 megabytes for this demo. Of course, if you have a big heap, let's say you have a gigabyte heap, then this has all be stored into files, right? So because it's in principle, you have to don't think about class files and stuff like that. If you create a checkpoint, it's a totally different file format, and it's really the state of the JVM that will be stored there, including your application running on it. Because when you restore, it really, what it does, it takes the JVM, stops it, puts it somewhere in the black hole, and then it takes it out and starts it again. The JVM has no idea what happened at all. So for the JVM, nothing happened. It just continues running. That's so it's not really a security thing here, I think. At least I don't see it where the problem is with security, because it's like stopping it and restarting it. So there's also no attack vector that you can use here, I think. At least not if you, maybe if you know how to hack the Creo files, but I think this is not really possible. Not so easy.
And one more question from Luis. Also, is it possible to select which J command to which part of JVM you want to checkpoint to avoid outdated read-through cache, for instance?
Yeah, like I said, you either can call J command calling your jar file, or you call it with a PID, and then it's clear what it is, right? So, and because you defined the folder where it should store the checkpoint, it shouldn't be a big problem to identify, and it's always the whole JVM that's running and your application that you started. I mean, if you run multiple applications in one JVM and then checkpoint it, oh, never tried that one. Now that might be worth trying. But usually it's really, you take the PID or take the jar file of your application and use J command on that.
I see. Thank you. I think we are in time, and it was really deep dive, really helpful. Thank you for joining. Thank you for support Ukraine in this difficult time, and have a nice day.
You too. Thank you.